Hello everyone, I'm Matthew Fishman. I'm an associate data scientist at the Flatiron Institute in New York. I'm the lead developer of the ITensors.jl package, and I'm going to give a brief talk about what's new in ITensors.jl. So to start with, I'll give a brief overview what iTensor is. So iTensor is a tensor library with a memory-independent and dynamic high-level interface. It supports dense, diagonal, and multi-threaded block sparse tensors and has a GPU backend, though for now that's only for dense tensors. You can think about tensor networks as a class of low-rank approximations for very high-order tensors. And on this slide, I'm just going to give a very brief overview of a contrast between standard Einstein summation notation and the iTensor interface. So you can see on the left side, I show an example from tensor operations of doing a series of tensor contractions which involve the same sets of tensors over and over. So you can see that it involves writing the same indices over and over, and it's easy to make a typo. For example, on the last line there's actually a typo, but it can take a long time to stare at these diagrams and see typos like that. So on the right hand side I show an example of the iTensor interface where you define your tensors with indices which have unique identifications, so then in every following operation, the indices contract properly with the correct indices on other tensors. And so you can see that you could get a much simpler interface for complicated tensor operations. And this is a schematic of the organization of the library, where it's built on top of a module called ND-tensors, which defines a variety of dense and sparse tensor operations. At the iTensor level, it defines this high-level contraction interface, and then we build up basic tools for tensor operations and tensor network operations, which we can then use to build high-level algorithms. And the iTensor library was originally in C++ and was ported to Julia starting in 2019 when I started working at the Flatiron Institute. In the history of the library, including the C++ version, there have been over 400 articles published using the software. And at this point, the Julia version is quite well developed, and we've released the 0.2 version in June of 2021. And I encourage you to check out our website and paper to learn more background on iTensor. In this talk, I want to give a very brief overview of a variety of new features, so I'm not going to go into depth about each one, but I just want to give people a flavor for what kind of development has been going on and where the package is heading. So there are features like multi-threaded block sparse contractions, GPU and T-Bliss contraction backends, a general quantum circuit simulator, a feature for optimizing the sequence of a tensor network contraction, a tool for visualizing tensor contractions, a tool for working with non-interacting systems of particles and translating them into tensor networks, and a tool for caching tensors on disk. And these are some of the more established features, but then I also want to talk about some more experimental features, such as automated handling of the fermion sign in tensor networks, tools we're working on for doing automatic differentiation to automate gradient-based optimization of tensor networks, tools for working with infinite tensor networks. So that would be low-rank approximations for infinite dimensional tensors, and then tools for working with higher dimensional tensor networks beyond one dimensional, which has been mostly the focus of ITensor up until now. So I'll just point out that in C++ we had block sparse multithreading, and we've ported that feature to the Julia version using the standard library threads module, and it was a very smooth process. Overall, it's been easy to use, and we've seen some pretty good speedups using the block sparse multithreading. There's more investigation we can do into multithreading other operations beyond tensor contractions, and adding other layers of contractions to make use of other layers of multithreading to make use of the composable multithreading, which we've done some experimenting with and has been quite successful, such as multithreading over sums of tensor contractions, which then have multithreading over blocks of a block sparse tensor contraction. So you can see here we have an example of contracting over 4 blocks of a block sparse tensor, and with 6 threads we see 3.5 times speed up. I want to point out that we actually had a GPU backend that was built by Katie Hyatt, who is now in the AWS Rocket team. And we've recently been working on updating that for ITensor 0.2, and we would like to start making sure that backend works with block sparse tensor operations. So far it has only been working for dense tensor contractions and decompositions. And we've also been experimenting with tbliss backend, which tbliss is one library which implements a generalization of gem to tensor contraction, so it involves a permutation-free tensor contraction, where we see reasonable speedups, though they haven't been high enough to justify using it as a standard backend yet. And I would also like to point out that we have an Octavian backend for fast tensor contractions of non-blast float element types such as integer or tropical numbers, which was contributed by a colleague, Jingguo. And we would like to continue investigating other high-performance tensor contraction backends. I want to point out a high-level quantum circuit simulator that we've added recently, which can do MPS or matrix product state-based gate evolution of non-local n-site gates. So here's a quick example of applying a layer of Hadamard gates and then a layer of control NOT gates to an MPS, and in a few lines of code you can run this circuit and then get samples of your state. And there's many project ideas generalizing and building off of this tool set. In collaboration with Giacomo Torlai, who's now at the AWS Center for Quantum Computing, we've built a package called PastaQ, which has a lot of high-level tools for quantum circuit simulation and tomography. I don't have much time to get into the details of it, but It allows simulating noisy quantum circuits, both state and processes, and learning noisy states and processes from data, such as data coming from a quantum computer, using state-of-the-art tomography techniques. And I encourage you to check out PastaQ.jl if you're interested in those kinds of things. One feature that I'm excited about is an interactive visualization tool called ITensors.jl, which is built on top of Makey and uses network layout to determine a starting layout for the tensor network. So essentially how it works is you define your tensor indices like normal, you define your ITensors like normal, and then in a tensor contraction in your code, you just add the @visualize macro, which runs your contraction code like normal, but then also pops up a Makey window with a visualization of the tensor contraction you're trying to perform. And I don't show it here, but you can click on the boxes and drag them around to make the visualization easier to see. And we would like to investigate using some alternative lighter weight backends which could be used by default in iTensor, and possibly doing things like generating TIX code for use with LaTeX, and there's a lot of more advanced features that we can investigate. Another nice feature that we've added recently is contraction sequence optimization. So when you have a tensor network where you're contracting 5 tensors like this, there's a question, depending on the dimensions of the indices in the network, which tensors you should contract first. For example, you could choose to contract C with D, or C with E, or A with B. And this is actually, in general, an NP-hard problem, but there's good heuristic algorithms for coming up with good sequences, particularly for relatively small networks. So we've added a automated sequence optimization, which you could just use from the contraction sequence optimization module in iTensors, and it outputs the contraction tree for the optimal contraction sequence, and then you can use that contraction sequence to speed up a calculation where you don't know what the proper sequence is. And there's a lot of work we could do on using better, more sophisticated backends for determining the sequence and caching across multiple diagrams. I'll discuss a little bit more about that later. A more physics-oriented feature that Miles Studenmeyer at Flatiron, along with a postdoc Jing Chen, have been working on is automatic fermion sign. So the idea is that for certain types of tensors that we come across in physics, when you do a permutation of a tensor index, you can, in general, introduce minus signs on some blocks of say a block sparse tensor. And so in the physics community, a lot of those minus signs have sort of been put in by hand, but in principle, if you track where all these permutations occur in your code, you can automate the insertion of those minus signs. And so we have some working code where if you do a permutation, it introduces minus signs, and I think the future is mostly working, but there's a few bugs to work out. So keep an eye out for that feature, and you can try out the current state of it at this branch of ITensors.jl. A feature that we're working on in conjunction with summer intern Linjan is automatic differentiation of tensor networks. So, for example, you might want to, this is a very simple example, but you might want to differentiate a tensor network where the tensors themselves are parameterized by a certain parameter, say beta, and we would like to compute the derivative with respect to beta, and we want to use automatic differentiation tools to automate this process for us, because as the tensor diagrams get complicated, it becomes very challenging to write these derivatives by hand. So the goal is to expand on a package that we have called ITensorsGrad.jl, which provides chain rules based primitives, which could be used with an AD code such as Zygote, which handles tracking the derivatives through a variety of operations. But when the tensor contractions become quite complicated, tracking the derivatives naively can become expensive. So it can be better to analyze the tensor network at a higher level, which we are using a package called AutoHoot, which is originally in Python, but Linjan has recently wrapped it in Julia in a package AutoHoot.jl, which does high-level analysis of INSUM type expressions, and then can do optimizations of those INSUM expressions and gradients with respect to those INSUM expressions. So we are working on integrating AutoHoot with ITensor so that we can make use of the simplifications that AutoHoot can do on gradients of tensor networks to help build more efficient primitives for AD of ITensor expressions. So keep an eye out for developments on those packages. I've also worked a little bit on a package ITensor Infinite MPS.jl for working with infinite tensor networks. So these are essentially low-rank approximations for infinite dimensional tensors. And so far, mostly I've just worked out a high-level convenient interface for working with an infinite tensor network where you define a subset of tensors that get repeated in a unit cell, and then by indexing out of that unit cell, you internally grab the same tensor but with some new labels that indicate which unit cell the tensors are in. And so I still need to work on getting some higher level algorithms for the interface working, such as variational optimization. But that's something that we'll be working on in the next year. Another package that I'm working on partially in conjunction with the work on automatic differentiation is a package called ITensorNetworks.jl, which provides tools for working with higher dimensional tensor networks. So, for example, tensor networks for 2D network geometries, or possibly more general network geometries. So this is an example of a short script which takes a 2D tensor network, and which might be intractable to contract on its own, and creates an approximation for this network by inserting low-rank projectors into the network. And this is a helpful primitive operation for being able to optimize this tensor network with automatic differentiation. So this package is at a very early stage, but we will be developing this in the coming months. Another package I'd like to point out is ITensor Gaussian MPS. This is also more of a physics-based package where it allows you in a few lines of code to convert a non-interacting quantum state into a tensor network, and this can be very helpful for speeding up the variational optimization of a tensor network if you believe that the state that you're targeting is close to a non-interacting quantum state. And finally, I'd like to point out a little package I wrote recently called serialized element arrays. So the idea for this package is if you have a collection of large tensors where collectively all of those tensors might not fit in memory, but you only need a small subset of them in memory at a time to do a certain operation, this gives a high-level interface for serializing the elements of this collection to disk, and then when you retrieve the elements with a call to get index, they're put into memory where you can do an operation such as a tensor contraction. And so we're using this currently in ITensors.jl for a write-to-disk feature to be able to perform tensor network contractions on tensor networks that don't fit in memory. And so there is future work on generalizing this to other data structures. For right now, we only support an array-like data structure, but we could support a dictionary-like data structure and perform automated memory caching of recently accessed elements, which would speed up accessing elements in certain situations. So I would like to conclude by just giving an overview of what we discussed, since I went through a lot of different topics. So some of the main new features in ITensor are multi-threaded block sparse, tensor contractions, GPU and T-Bliss contraction backends, as well as Octavian backends, a general quantum circuit simulator, a feature for automating the optimization of the sequence of a tensor contraction, a tool for interactively visualizing tensor contractions, a tool for creating the tensor networks for a system of non-interacting particles, and a tool for automatically for caching a collection of tensors on disk if you're running out of memory. And some works in progress are automating keeping track of the fermion sign for fermionic tensor networks, adding high-level tools for automatic differentiation for gradient-based optimization of tensor networks, tools for studying infinite tensor networks, and higher dimensional tensor networks. So thank you for listening. Please check out our iTensor related packages.